Broadcasting live from our Center Hall studios. Here is Dr. Royer discussing differentials and differentiability. So put your hands together for Dr. Royer. I'd like to review a topic from Calculus 1. It's in section 3.9. The topic is differentials and linear approximation. So the starting point is that we have a curve, a function of one variable, y equals f of x, and we have a particular point in mind, point A, where we've taken x naught, a number, and put it into the function and gotten f of x naught. Now, for whatever reason, we want to change the input by an amount delta x. And so if we change the input, of course we change the output. That's going to take us from point A to point B. And the difference between the outputs here is a quantity that we're going to call delta y. And we're interested in being able to easily compute delta y. Now, for a number of reasons, one of which is that it is easier to compute in many situations, and sometimes the only thing that can be computed, we often talk about a related quantity. So that comes from considering the tangent line at point A, drawn here, and then following that tangent line out until the x-coordinate has been changed by the amount that we've been discussing, and that gives us point C. And then we start discussing this difference, and we'll call that dy. And you can see that if delta x is small, then dy will hopefully be a pretty good approximation to delta y. So let's see if we can compute or figure out how to compute this dy. Let's take point slope form for the tangent line. So remember, if you know the slope of a line and you know a point on the line, you can write down an equation for the line. It goes y minus, and now a y-coordinate of a point on the line here at point A is f of x naught, equals the slope of the line, which is going to come from the derivative f prime of x naught, times quantity x minus the x-coordinate of a point on a line. So x and y are the variables here, x naught and y naught, and f prime of x naught are specific numbers for a specific problem. Okay, let's agree to identify the notation delta x and dx and say they're the same thing, and it's right here. And now if you think about it, dy divided by dx, change in y divided by change in x, is slope of this line. And so if I identify this number as, or expression as dy, then dy divided by dx equals f prime. That's the derivative, and so that's consistent with the picture above. And so in simpler notation, here it is, dy equals f prime of x naught times dx. This is called the differential. And it's similar to the derivative. If I took both sides and divided by dx, then I get dy over dx equals f prime. If dx went to 0 in the limit, I would get the derivative. So these are very much related concepts. But you can think about dy as being a small change in y, or an approximation of a small change in y, and dx is a small change in x. Okay, that was in one dimension. Now let's flip over and talk about the same concept for a function of two variables. Here's a surface, f of x, y, and let's say that the y-axis is along here and the x-axis is along here. And let's let the third variable be the output. So z can be given as some function of x, y, as described by this surface. Now, I pick some point that I'm especially interested in, say right here. And I talk about its coordinates as x naught, y naught. I take those values of x and y and plug them into the function. In other words, I go up until I hit the graph of the function, say right here. And so this point is x naught, y naught plugged into function f. And I guess if I want to write it as a ordered triple, it's x naught, y naught, and then z equals f of x naught, y naught. Okay, so here's my point that I'm interested in, and now I want to change x and y a little bit. Ignore the yellow plane for a moment. I'm about to get to that. So I want to change x by a small amount, delta x, and I want to change y by a small amount, delta y, not necessarily the same as delta x. And so that moves me to a new point here, x naught plus delta x, y naught plus delta y. And now I plug that into the function. So I go up until I hit the surface. And now I'm interested in discussing the difference in these two levels, where I hit the curved surface the first time and where I hit the curved surface after I changed the input. So let's call this delta z, and I'm interested in approximating delta z. An expression for that is here, f of the new inputs minus f of the original input. Okay, one way of approximating that change is with a linear approximation. In one dimension, when we want to approximate a curve with something that is linear or straight, it's a tangent line. If the surface that I'm discussing is smooth, a way of approximating a curved surface is with a tangent plane. So back to this original point on the curved surface that I was interested in discussing, I can put a plane there that is tangent to the surface, or touches the surface at just that one point, and I'll say that is the tangent plane. And now I can take the new input that I'm discussing, and by the way, when I take the old input, or the original input, and plug into the function, I hit both the tangent surface, or the surface and the tangent plane at that point. I mean, that's why it is the tangent plane, because it touches, it has the same coordinates at that point. But now once I go over here, if I plug the new input into the surface and the new input into the equation for the tangent plane, I hit at two different points. So when I go up from here, I hit the tangent plane right here, and now I can discuss, let's go clear out here, I guess. Now I can discuss this quantity, let's call that dz, it's the change in the tangent, in the level of the tangent plane, as an approximation to delta z, which is the change in the level of the surface. And we'll not take the time to do it, but by analogy you can show that the expression for delta z, for dz rather, is take the partial of f with respect to x and plug in the original point, multiply by the change in x, and now add, take the partial with respect to y, plug in that original point, and multiply by delta y. This again is called the differential. It's called the total differential, actually. And notice that it involves both changes in x and y, and it will require the usage of both partial derivatives. But if I just take one piece of this, say the first term, it's exactly what we had before in the one variable case. So it's basically just doing what we did up above twice and then adding the changes together. And again, we're going to be talking about using dz as an approximation to delta z. Okay, first example. Suppose that I have a right circular cylinder and I measure its radius and height. And of course I'm going to use my, if I want to know volume, I'm going to use my usual approximation, pi r squared h. But when I take physical measurements like this, I make measurement errors. It's unavoidable. And so I'm going to think about those measurement errors as being an actual change. It's not that I'm trying to make this change, but that reality is different than my measurement, and I'm going to think about that as, okay, I take my measurement and then I'm going to change my measurement a little bit, if I could, to actually reflect the real measurements. And notice everything is given as a percentage here. So let's talk percentage. The change in the measurement of the radius, or the error in measurement of radius, let's call that delta r. And to convert it to a percentage or a proportion, I'll divide by r and take the magnitude. What we're given is that this is within 2%, or less than or equal to 0.02. We're also given a similar expression on the reliability or accuracy of our height measurement. That was accurate to within 5%, or 0.005. And I would like to find, or a better word would be approximate, delta z divided by z. Find the resulting, not z, v. Sorry about that. Approximate delta v divided by v, which is the percentage error or proportional error in volume. Okay, this is going to be approximated by dv over v. So let's see if we can compute that expression. Here is v. It's v as a function of r and h. So I'll just recopy that. V as a function of r and h is pi r squared h. And now let's start computing the differential dv. Okay, from our discussion above, it should be partial of v with respect to r times delta r plus partial of v with respect to h times delta h. And if I take my partial derivatives differentiating with respect to r, this is 2 pi r h. And differentiating with respect to h, this is pi r squared, then times the delta h. So those first partials were easy to compute. And now back to dv over v in magnitude. This is what I'm interested in. This is 2 pi r h delta r plus pi r squared delta h divided by pi r squared h. Take magnitude. And even though I don't know any numbers in the problem, I don't know r or h or delta r or delta h, notice that some cancellation here can occur. Let's put each term of the numerator separately over the denominator, and what we get for the first term then is 2 delta r over r, and what we get for the second term is delta h over h. And now those start looking friendlier because I do know something about delta r over r and delta h over h. Okay, let's use something called the triangle inequality. When I add two things together and then take their absolute value, that's less than or equal to taking the absolute values first and then adding together. It just removes the possibility of positive-negative cancellation, keeping the quantity from getting large. And now if I work out what this is, the 2 can come out of the absolute value, and delta R over R was less than or equal to 0.02, and delta H over H was less than or equal to 0.005. And so if I add these two things together, I get 0.045, which is 4.5%. So what I've confirmed is that the error in volume caused by measurement error in the radius and height is going to be less than or equal to 4.5%. Notice that I really couldn't compute delta V in this problem because I don't have, I was never given numbers in this problem, a specific value for the radius and for the measured height. Okay, so that's one application problem for differentials, and now let's go on and talk about the very much related concept of differentiability. Review again from Calc 1 for just a moment. We'll say a function y equals f of x is differentiable at a certain point if the derivative exists at that point. And remember that if a function is differentiable at a point, then its graph is going to be smooth at that point. In particular, if a function is differentiable at a point, then it has to be continuous at the point. The other way around is not necessarily true. So in higher dimensions, let's see if the same thing applies. Well, first of all, there are two partial derivatives now to discuss. If f is a function of x and y, there's partial f partial x and partial f partial y to discuss. Let's look at this weird definition. Here's x, y, z. Now I want to talk about the function of two variables that's 1 if x times y equals 0, and it's 0 if x times y is not equal to 0. Well, there's only one way that x times y can equal 0. That's if that's if at least one of the variables is itself 0, or in other words, that I'm on a coordinate axis. And so the graph of this thing is actually 1 when I'm plugging in a value that is on a coordinate axis, and it's 0 if I plug in a value that's not on a coordinate axis. So the graph is a cross. This is a plus sign, an infinite dimensional, a plus sign of infinite extent, whose crossing is right above the origin. And then everywhere else, the value of the function is 0. So I'm not even sure how to draw that, but the values of the functions out here are sitting on the xy plane. The z value is 0. And then just along the coordinate axes, it jumps up to the value 1. So let's answer some concept questions here. Is f continuous at the origin? Well, absolutely not. There are places arbitrarily close to the origin where the value of f is 0, but right at the origin the value of f is 1. So no, not a chance. Now, do the first partials exist at the origin? Well, for that I have to think about the values of the slope as I come in toward the origin. And if I think about fx for a moment, then I want to talk about values of f of x comma 0 minus f of 0 comma 0, or maybe better, delta x over delta x. This is the difference quotient that's going to lead me to the value of the derivative in the limit. But over here is a point with y coordinate equal to 0, as it is in this discussion, and x coordinate a small positive number. And here is what I get when I plug 0, 0 into the function. And you see this difference is 0. Both of these values are 1. The difference is 0. And so and the same thing happens if I go over to the other side and if I get closer and so on. For this quantity here, I'm always getting 0 in the numerator, and so 0 for the fraction, and so 0 for the limit, and so 0 for the derivative. So in fact, yes, the first partial of f with respect to x does exist, and I just noticed that I was putting dots on the y-axis and talking about the x-coordinate. So these dots actually should have been located along here. And then the conclusion still holds that the first partial of f with respect to x is 0. Likewise, the first partial with respect to y is 0. So in particular, yes, they do exist. And now, here's something weird. Both partials exist at the origin, and yet the function is not continuous at the origin. That's different than what we said up here. Before we said that if the derivative existed, then the graph would have to be smooth, and in particular it would have to be continuous. So the situation for functions of two variables is a little bit more complicated than for one variable. What we've commented here is note existence of the partial derivatives fx and fy at a point is not enough to guarantee differentiability. And continuity at that point. So the partials can exist at a point, and the function can still be not smooth. In fact, it can even be not continuous. So here is what we're going to require in order to discuss a smooth graph, or here are the conditions for what we're going to do when we say a graph like this is smooth. We'll say the function is differentiable at a point if two things. One is that both partials exist at that point. We already said that's not enough, so what else do we need? We're going to ask that the tangent plane be a good approximation near this point. And we just earlier discussed what we mean by a tangent plane approximation. So then very specifically, very technically, what does it mean for the tangent plane to be a good approximation? It means that the difference between the actual change in z and the change of the tangent approximation can be written this way as some number epsilon 1 times delta x plus epsilon 2 times delta y for some quantities epsilon 1 and epsilon 2 that both go to 0 as we approach the origin. Here's a completely equivalent way of saying the same thing, that this particular limit equals 0. Let's do an example using both. You actually only need to use one of these two checks. They are the same check. So show that z equals x cubed plus 3y is differentiable in the sense we've just discussed everywhere in the plane. And so I need to be talking about the partial derivatives existing. They certainly do. This is a polynomial. So first of all, fx and fy exist everywhere in the plane for every value of x and y. Now let's discuss the other part, and I'm going to discuss the delta z minus dz piece. So what is delta z in this problem? By definition, it's f of x plus delta x comma y plus delta y minus f of xy. And if I plug those expressions into the specific function we have, x plus delta x cubed plus 3 times y plus delta y minus x, not cubed but squared, minus x squared plus 3y. And if I expand this binomial and then cancel everything that I can, I end up with 2x delta x plus quantity delta x squared plus 3 delta y. And this should be a plus sign here, making typos. Okay, that's delta z. How about dz? Well, that's partial derivative of f with respect to x times delta x plus partial derivative with respect to y times delta y. And that is 2x delta x plus 3 delta y. So now I'm supposed to talk about delta z minus dz. So if I take the difference, 2 out of the 3 terms cancel, and all I'm left with is quantity delta x squared. And so now the question becomes, can I write this as an epsilon 1 times delta x plus an epsilon 2 times a delta y? And the answer is yes, of course. If I let epsilon 1 equal delta x and epsilon 2 equal 0, and plug those in here, then I have expressed delta x quantity squared as this combination of delta x and delta y. And the first way of checking was, okay, do those values of epsilon 1 and epsilon 2 approach 0 as delta x and delta y go to 0? Well, yes. Delta x goes to 0 as we approach the origin. That should be obvious. And 0 goes to 0 as we approach the origin. And notice that this happened for every value of x and y. I never specifically chose numbers for x and y. So we have shown we've shown that dz well approximates delta z everywhere in the plane. And thus, when I put together the two facts, number one, that the first partials existed everywhere in the plane, and number two, that the difference between the change in function value and change in tangent plane is controlled, is small in this sense. Thus, f is differentiable everywhere. So that finishes the problem. Just for the sake of illustration, let me replace this discussion of the epsilons with usage of condition number 2. That says, let's look at a limit as we approach the origin of. Upstairs is the change in, or the difference between delta z and dz, and downstairs is just the size of the vector delta x, delta y, or in other words, how far are we away from the origin at a point of discussion. So if we look at delta z minus dz over magnitude of the vector delta x delta y, we get the following. We already computed delta z minus dz. That worked out to just be delta x quantity squared. And downstairs, the length of this vector is square root of delta x squared plus delta y squared. Okay, I want to discuss whether this thing has limit 0 as delta x and delta y go to 0. If I immediately just plug in delta x equals 0 and delta y equals 0, I get my usual 0 over 0 problem. Perhaps from Calc 1 you remember the so-called squeeze theorem. And that's to say that if I can squeeze or sandwich theorem is another name for it, if I can sandwich this quantity in between two quantities which have the same limit, then this guy in the middle also has that limit. So let's start talking now size of this, magnitude of this. And on the one hand, once I take the magnitude, this quantity is obviously greater than or equal to 0. And let's try to sandwich by something on the other side. I'm going to be trying to bound this by something that is larger. So if I look at a fraction, remember to make a fraction larger, I can make its denominator smaller. I propose to just ignore this term in the denominator. It's a positive term, or non-negative term, obviously. Delta y quantity squared is greater than or equal to 0. So if I ignore it, the denominator is going to get smaller and the fraction is going to get larger. So this thing is less than or equal to delta x quantity squared divided by square root of delta x quantity squared. And what is this? Well, I have downstairs now I have just delta x, or magnitude of delta x, and upstairs I have magnitude of delta x squared. So this cancel one factor, and this works out to be magnitude of delta x. Now, I'm trying to show that my limit was 0, and the squeeze theorem said if the thing on the left has limit 0, and the thing on the right has limit 0, then the thing in the middle has limit 0. And all of that is true. 0 goes to 0, and delta x goes to 0. These are both as we approach the origin. And so, by squeeze theorem, the limit as delta x and delta y approach the origin of this expression delta x quantity squared over square root of delta x quantity squared plus delta y quantity squared equals 0. And again, then we have shown that dz and delta z are sufficiently close together and f is everywhere differentiable. So there was a repetition right here, and you can either, in any given situation, you can choose to do the problem this way with the epsilons or this way with this limit. Finally, here is just something that's very true and very powerful. So it turns out that if both first partials are continuous on an open region containing a point, then f is differentiable at that point. And so here's an even better way to show that a function is differentiable. Rather than messing with epsilons or this limit, the first thing that I would try is to show that the partials are continuous on an open region. Now, a little while ago, we just said that existence of the partial derivatives at a point is not enough to guarantee continuity at that point or differentiability at that point. And that's true. But having the derivatives be continuous on a region is stronger than having the derivatives be continuous at a point. So what we're saying here is, here's some particular point x naught, y naught that I'm interested in discussing. And here is some particular region, open region, surrounding that point. If I can show that the partial of f with respect to x and the partial of f with respect to y are both continuous everywhere in this region, then that shows that the function f is differentiable at that point. And that usually is an easier way to show things than working with the definition above. Here's another important thing. If a function is differentiable at a point, then it is continuous at that point. And differentiable now means, again, as we've just been discussing. So, example, where is this horrible, horrible, horrible looking function differentiable? If I come back here and try to work with either of these definitions, I think it's a rather discouraging process. But let's look at this. First of all, this expression is built out of polynomials, x's and y's, exponentials, e to the x, y, and sinusoids, sine and cosine. Those function classes are everywhere continuous. They're always continuous. Second of all, the denominator x squared plus y squared plus 4 to the 5/6 power is always going to be a positive number. X squared and y squared are greater than or equal to 0. Now I add the 4. I'm always positive, no matter what I choose for x and y. So there's no danger of division by 0 or taking an even root of a negative quantity. So this function is very well defined everywhere. And if let's write that down, f is everywhere continuous. And now let's not do it, but let's mentally think about what would happen if we took the first partial with respect to x. I start using the quotient rule, and then inside that I would have to use the product rule and the chain rule in a very, very messy sort of way. But what happens when you differentiate polynomials? You get more polynomials. What happens when you differentiate exponentials? You get more exponentials. And what happens when you differentiate sinusoids? You get more sinusoids. And so, without writing down the exact expression for first partial of f with respect to x, it's going to look something like this. It's going to be built out of polynomials, exponentials, and sinusoids, which are everywhere continuous. So we can just say that first partial of f is everywhere continuous. It also consists of polynomials, exponentials, and sinusoids. And then by the same argument, the first partial with respect to y is everywhere continuous. Okay, so now I come back to this part of the theorem and say the first partials, both first partials of f are continuous everywhere in the plane. So on any open region. And therefore, no matter what point I pick, I can certainly say that the first partials are continuous at and nearby that point, and so f is differentiable at that point, and it's differentiable at every point. And so the answer to the question, without really doing any computation, is that f is differentiable everywhere in the plane. And its graph will be smooth everywhere in the plane. And that concludes what I have to say about this topic. Thanks.